Imagine for a second that you need answers to an incredibly complex problem.
Hmm.
And, for years, the approach to AI was basically well, to climb a mountain, enter a dark cave, and consult this single omniscient oracle.
Right.
You ask one question, you wait, and you get one incredibly detailed answer.
Yeah, it's a really vivid image. And I mean, it perfectly captures the reality of the AI landscape back in 2023.
Oh, absolutely.
We were dealing with one massive model, one prompt from a user, and one sequential response. The entire industry was essentially built around supporting that exact interaction.
But flash forward to today. It is March 2026.
Yeah.
You don't climb the mountain anymore to talk to a single oracle.
No, you definitely don't.
Instead, you walk into a bustling 50-story corporate skyscraper. You hand your problem to a manager. That manager hands it off to a researcher who pulls data and passes it to a fact-checker.
Who routes it to a compliance officer.
That's exactly. Who finally hands off the verified data to a writer. You have hundreds of specialized AI workers all talking at once, passing notes, debating, and collaborating in real time to build your answer.
And that transition from the isolated oracle to the digital skyscraper is, well, it's arguably the most significant shift in computing we've seen this decade.
Yeah.
And it has completely broken the physical infrastructure we built for AI. Because as it turns out, the machines engineered to power a solitary oracle are just fundamentally terrible at running a chaotic, collaborative skyscraper.
Which brings us to today's deep dive. We are looking at a stack of highly confidential engineering documents, market briefs, and pitch decks from an AI hardware startup called Cortexpod.
Yes.
And the mission of this deep dive is to explore Cortexpod's incredibly bold, contrarian bet. They are claiming that the undisputed king of AI hardware, the all-powerful NVIDIA GPU, specifically chips like the H100, is actually the wrong tool entirely for the future of AI.
I mean, making a claim like that against the biggest incumbent in the space is massive, but their timing is really deliberate here.
How so?
Because here, in early 2026, we have just crossed a critical threshold that the industry calls the inference flip.
The inference flip.
Right. For the first time, inference, which means actually running the models to generate responses for users, now consumes over 2/3 of all global AI compute.
Wow. Over 2/3.
Yeah, it has officially overtaken the training phase. The models are trained once, but they are queried billions of times a day.
That makes sense.
So the market has shifted entirely to execution, and Cortexpod is basically betting their silicon that the underlying hardware hasn't caught up to how that execution actually happens now.
Okay, let's unpack this. Have you noticed how AI isn't just a single chatbot answering a single question for you anymore? When you look at the enterprise world of 2026, we are fully living in the era of agent meshes.
Yeah, and to really grasp Cortexpod's argument, we should look at the primary case study in their documents. It's a 32-agent loan application pipeline currently running at a major bank.
Okay, lay it out for us.
Imagine a dense 200-page financial document being submitted. In an agent mesh, this document isn't just ingested by one large language model.
Right.
It's processed simultaneously by a router agent, a researcher, a fact-checker, a compliance auditor, and a summarizer. They're all running concurrently.
At the exact same time?
Yes, looking at the exact same context and constantly handing off intermediate thoughts and data to each other in milliseconds.
And this is exactly where the physical hardware hits a wall. Like, NVIDIA's H100 is an absolute marvel of engineering. No one disputes that.
Absolutely.
But Cortexpod's documents argue it was structurally designed for that 2023 world. When you try to force this modern 32-agent mesh onto a GPU, you slam into three massive bottlenecks. Let's start with the first one, context capacity.
So the context capacity issue is deeply tied to how GPUs actually manage memory, even when you use advanced software partitioning.
Like CDMPS.
Exactly, CDMPS, which is essentially NVIDIA's software layer trying to slice up the GPU to handle multiple tasks. Even with that, an H100 maxes out at about 8 concurrent model contexts.
Just 8.
Just 8. If you push it to 9 or 10, it runs out of active memory and has to start swapping data in and out of storage.
Oh, wow.
But remember, our bank's pipeline doesn't need 8 contexts. It needs 32, or in some larger meshes, 256 simultaneous active agents.
So the software is trying to juggle, but the hardware keeps dropping the balls.
That's a good way to put it.
And that leads to the second bottleneck, which is handoff latency. I want you to picture a chef in a kitchen trying to cook 8 entirely different, highly complex meals on a single stove.
Okay.
Every single time they need to switch from, say, stirring a delicate soup to searing a steak, they have to pack up all their current ingredients, put them back in the fridge, scrub the cutting board spotless, and pull out entirely new ingredients.
That sounds exhausting.
Right. In the GPU environment, taking the context from Agent A and handing it to Agent B means routing the data out of the chip through a host computer's software scheduler and then back in. That switch takes about 50 to 200 milliseconds every single time.
And, 50 milliseconds might sound instantaneous to a human, but in computing terms, it's an eternity.
Yeah.
Keep in mind, these agents in the mesh are handing off thoughts to each other dozens of times per second. If you have 10 handoffs between the researcher, the fact-checker, and the writer, that adds up to 2 full seconds of pure coordination delay.
2 whole seconds of just waiting.
Exactly. You are waiting 2 seconds before a single word of the actual answer is even generated. It's the equivalent of office workers spending 90% of their day just walking between desks to hand over a single piece of paper.
Which sounds incredibly inefficient. But the third bottleneck they highlight might actually be the most painful, and it comes down to redundant computation.
Right, the redundant reading problem.
Yeah, let me ask you this. If the researcher, the fact-checker, the auditor, and the summarizer all need to read that exact same 200-page regulatory filing we talked about, does the GPU realize they're looking at the same document?
That is the crazy part. It doesn't.
It doesn't.
No, the GPU architecture treats every single agent as an isolated silo. So when an AI reads a document, it creates something called a KV cache, or key value cache.
Like a scratch pad.
Exactly. Think of this as the AI's complex scratch pad or short-term memory of the document. Computing the scratch pad takes a lot of math and a lot of memory.
Right.
If 4 agents read the same document, an H100 cluster computes that massive scratch pad 4 separate times.
Oh, man.
Cortexpod calculates that this wastes roughly 63 gigabytes of highly expensive video memory just to read the exact same text 4 times.
What's fascinating here is that Cortexpod's engineers exhaustively profile all of this, and their conclusion is stark.
Yeah.
These are not software bugs.
No, they're not.
You cannot fix this by just writing better code or a more clever algorithm. These are fundamental architectural constraints.
Yes.
The memory subsystem of a GPU was brilliantly designed for sequential, large batch, throughput-like, blasting through one massive problem at a time. It was never designed for dozens of independent digital workers rapidly swapping small chunks of information.
And you simply cannot fix a hardware bottleneck with a software patch. The physical pathways on the chip just aren't routed for that kind of traffic.
Which explains why Cortexpod didn't bother writing a software patch.
Right.
They went straight to the silicon. They decided to build a custom 12-nanometer inference chip, explicitly designed from the ground up for these collaborative agent workflows. They call it the CortexChip.
And the absolute heart of the Cortex chip, the thing that makes it entirely different from a GPU, is a dedicated piece of silicon they call the CMFC, or the Cortex Mesh Fabric Controller.
The CMSC?
Yeah. It acts like a brilliant traffic hop built directly into the metal. It completely bypasses those 3 limitations.
So how does it handle the capacity issue?
Well, instead of juggling 8 concurrent slots before the memory gives out, the CMFC handles 256 concurrent agent context slots natively.
Natively? Wow.
Right, it doesn't need software to slice up the memory. The hardware itself is pre-divided into 256 permanent desks for the agents to sit at.
And what about our chef constantly putting ingredients in the fridge? How does the custom silicon handle that handoff latency?
Because the agents all have their own permanent desks on the chip, they don't have to pack up their ingredients. The CMFC takes that 50 to 200 millisecond delay and crushes it down to under 2 milliseconds.
Under 2 milliseconds.
Yes. It achieves this because the handoff never leaves the chip. It doesn't have to ask a host computer's software scheduler for permission. The data transfer happens directly on the chip's internal fabric at roughly 1 terabyte per second.
That is an unbelievable speedup.
Yeah.
And looking at the documents, they also tackle that redundant reading problem, the 63 gigabytes of wasted memory, with something called a hardware-shared KV cache. How does that physically work?
So they use what's called a share read bus. Instead of 4 agents wasting memory to process the same 200-page financial filing, the CMSC designates 1 agent to compute the short-term memory scratch pad. That takes up about 21 gigabytes. Then instead of copying it, the chip uses a hardware broadcast bus. It essentially broadcasts that memory to the other 3 agents simultaneously in under 200 nanoseconds.
That's crazy fast.
No complex software orchestration is required at all. The physical hardware just inherently understands that multiple agents are looking at the same data, and it eliminates 75% of the redundant computation automatically.
Here's where it gets really interesting. If you flip through their pitch deck, you eventually land on the official Cortexpod logo.
Oh, yeah. I love this part.
It's an illustration of a human brain, but it's divided into 6 distinctly colored lobes: blue, green, orange, purple, dark gray, and red. At first glance, it just looks like a trendy tech startup graphic. But the engineering documents point out that this is a literal schematic of their technology.
Yes, and it's a brilliant visual metaphor. Each of those colored lobes represents a specialized agent hard-coded into the workflow. One lobe is the router taking in the request, another is the researcher pulling data, another is the compliance checker. They are operating in parallel, sharing context instantly, and producing a cohesive result that no single lobe could achieve on its own.
It's the brain as a distributed system rather than a single oracle.
Exactly.
But I have to push back here.
Okay.
Because when you look past the brilliant architecture and look at the actual physical hardware specs they are proposing to manufacture, it looks like they're taking a massive step backward.
How so?
For instance, they are using GDDR7 memory, which runs at 1 terabyte per second. NVIDIA's H100 uses HBM3E, which runs at a blistering 3.35 terabytes per second.
Right.
Plus, Cortexpod is building this chip on an older 12-nanometer process node, while the rest of the industry is spending billions fighting over cutting-edge 5-nanometer or 3-nanometer tech. Are they just settling for worse hardware because they are a startup?
I mean, on paper, comparing the spec sheets side by side, it absolutely looks that way. But the engineering logic behind it is actually incredibly sound. Yeah, you have to remember a fundamental rule of AI inference. It is bound by memory bandwidth, not by raw compute power.
Meaning the chip's ability to do math is faster than its ability to fetch the numbers to do the math on.
Precisely. If you put this specific agent mesh workload on a cutting-edge 5-nanometer chip, you are essentially buying a massive amount of computational power that is just going to sit completely idle.
I see.
It will finish its math instantly and then sit there waiting for the memory to catch up and hand it the next batch of data. A faster processor doesn't help if the highway feeding it is jammed.
Okay, that makes sense for the processor node.
Right.
But they still have a much slower memory highway. Their GDDR7 memory is moving data at 1/3 of the speed of NVIDIA's HBM. How do they make a slower memory standard work for cutting-edge complex AI?
So they bridge that gap using a technique called W4A8 quantization.
W4A8.
Right. To understand this, think of quantization as aggressive rounding. Let's say you have a highly precise number, like 3.14159. If you round that down to just 3, you save a lot of space, but you lose some nuance. Cortexpod takes the AI model's internal weights, which are usually 16-bit numbers, and aggressively rounds them down to 4-bit numbers while keeping the active thoughts at 8 bits.
So they are shrinking the physical size of the AI's brain.
Exactly. They shrink the model's memory footprint by a factor of 4. And here is the magic trick. If you shrink the data that needs to be moved by 4 times, a 1 terabyte per second memory pipe effectively feels like a 4 terabyte per second pipe.
Oh, wow.
By compressing the data, they completely neutralize NVIDIA's expensive memory advantage.
But there is no free lunch in physics or computing.
Very true.
If you aggressively round off the AI's knowledge, you have to lose something. Does the AI get dumber?
It does, and the Cortexpod documents are refreshingly impartial about this trade-off. When they put this compressed chip through standard AI intelligence tests, specifically the MMLU benchmarks using massive models like Llama 370B, they found the W4A8 quantization drops the model's accuracy by about 1.4 to 1.8% compared to running it uncompressed.
Now, a 1.8% drop might not sound like a lot if you're asking an AI to write a poem, but in an enterprise setting, like scanning a 1,000-page merger agreement, that drop in accuracy could be a total deal breaker.
Which Cortexpod anticipated.
Oh, they did?
Yeah. To counter this, they built something called hardware calibration assist registers directly into the chip.
What do those do?
Think of these registers as a dynamic, hardware-level spell checker. During the inference process, these registers actively monitor the math and dynamically adjust the scaling multipliers layer by layer, catching the most important nuances that were rounded off.
That's clever.
This hardware trick recovers about 0.3 to 0.5% of that lost accuracy.
So they claw back just enough intelligence to make it viable.
Yes. For analyzing legal contracts or reviewing financial documents, this puts the accuracy well within acceptable enterprise thresholds.
Got it.
Though, to their credit, the pitch deck is very upfront that for safety-critical applications, like a medical AI diagnosing a patient careful validation, is still required before you'd ever deploy a compressed model.
So, to summarize their hardware, they've built a highly specialized, slightly compressed, distributed brain. But if they have to do all this hardware trickery to make an older, slower chip work, does anyone actually want this?
Well, if we connect this to the bigger picture, it turns out the undisputed king of the hill is feeling the exact same pressure.
NVIDIA.
Yeah. Just a few months ago at the GTC 2026 conference, NVIDIA made a massive announcement.
Right, Dynamo OS.
Exactly. They announced a new system called Dynamo OS. This was NVIDIA's attempt to disaggregate inference. They proposed splitting the AI workload across two entirely different chips.
How does that work?
They're using their Vera Rubin chips for the prefill phase, which is reading the user's prompt, and then handing off the decode phase, which is actually generating the words, to a completely different piece of hardware called a Grok LPU.
Wow.
And they are stitching these two different chips together with software.
Wait, think about what that means. NVIDIA is the incumbent monopoly. And they just stood on a global stage and publicly admitted that a single GPU architecture can no longer efficiently handle the modern inference workload natively.
Yep.
They are trying to patch the problem with a complex multi-chip system.
By doing that, they are entirely validating Cortexpod's foundational premise.
No.
The single GPU is hitting a wall.
But does NVIDIA's Dynamo OS actually solve the problem Cortexpod is targeting?
It solves the efficiency problem if you are only generating one single stream of text.
Okay.
But it completely fails at the agent mesh level because Dynamo OS is still just a software orchestration layer.
I see where this is going.
Every single time your researcher agent needs to hand off context to your compliance agent, it has to cross that software scheduler to move between the different chips.
Which brings back the delay.
Exactly. As we discussed earlier, that adds 500 milliseconds to 2 seconds of pure coordination overhead per document. CortexPod solves this natively inside a single piece of silicon in under 20 milliseconds total.
So NVIDIA is trying to patch this problem with Dynamo OS, but they're still trapped in this high-cost, high-power multi-chip paradigm.
Right.
Which begs the question, who is actually desperate enough to buy a completely unproven custom architecture from a startup? CortexPod's documents lay out an incredibly specific business strategy. Asia first.
To understand why, you have to look at the economics of running these new AI systems.
Let's do a thought experiment. Imagine you are a startup CTO in Vietnam or India or Indonesia, and you have a $3 million infrastructure budget for the year.
Okay.
To run a 256 agent mesh using NVIDIA standard hardware, you need 32 H100 GPUs. That is going to cost you roughly $960,000 just for the hardware, and it is going to draw a staggering 22,400 watts of power.
Which is an enormous barrier to entry for any company outside of the massive Silicon Valley tech giants.
Huge.
But with CortexPod, you replace that entire 32 GPU cluster with one single Cortex chip. It draws just 300 watts, and it costs $3,000.
Wow. So you are trading almost $1 million in hardware for a $3,000 chip, just by changing the architecture to match how the software actually works.
Yes.
That completely changes the barrier to entry. So what does this all mean for the global market? Because there is a massive geopolitical shadow hanging over all of this that makes that price tag even more important.
Oh, absolutely. The regulatory landscape in 2026 is arguably the biggest driver of CortexPod's strategy.
Tell me about it.
In January 2025, the U.S. implemented the AI diffusion rule. This severely capped the export of high-end NVIDIA GPUs to Tier 2 countries.
Right.
Vietnam, India, Indonesia, Thailand, they are all restricted under this rule. Even if that startup CTO in our example actually had the $1 million to spend, they might not be legally allowed to buy the H100s, or they would be stuck at the back of an 18-month allocation queue.
And it is a double-edged sword for these companies. While the U.S. is restricting the hardware coming in, these same Asian countries are passing incredibly strict data sovereignty mandates. You have laws like NGET 13 in Vietnam, the Digital India Act, and DPDP in India, the MAS guidelines in Singapore. If you are a bank or a healthcare provider in these countries, you are legally forced to process your citizens' data locally.
Right, you have to keep it in country.
You cannot just send your customers' financial data to a U.S. hyperscaler cloud in California to get around the GPU shortage.
Exactly. You must process the data locally to comply with your own government, but you can't buy the high-end GPUs to do it because of U.S. export controls.
It's a trap.
It is an impossible situation for Asian enterprises. And this is where Cortexpod's seemingly backward technology choices become a masterclass in strategic geopolitical positioning.
Wait, let's connect the dots here. The 12-nanometer process node we thought was a weakness.
It is actually their greatest strength. Let's pause on how modern chips are made.
Okay.
Every high-end NVIDIA chip relies on something called CoWoS, which stands for chip on wafer on substrate. Right. It is incredibly complex, advanced packaging required to glue fast memory directly to the GPU. And because a company called TSMC in Taiwan is virtually the only one who can do it at scale, it is a massive global bottleneck.
So if you rely on TSMC, you are at the mercy of their waitlist and the geopolitical tensions surrounding Taiwan.
Precisely. By choosing older 12-nanometer tech, which can be manufactured by Samsung or Global Foundries,
Oh, I see.
and using standard BGA packaging, which is basically how normal chips have been packaged for years, Cortexpod completely bypasses that TSMC CoWoS bottleneck.
That is so smart.
They have zero reliance on it. They're structurally immune to the supply chain anxieties and export controls that are keeping executives in the Asia-Pacific region awake at night.
It is brilliant when you look at it from that angle.
Right.
They didn't just engineer a piece of silicon to solve a software problem. They engineered a chip to bypass a global geopolitical roadblock.
Yeah, they recognize that in 2026, AI infrastructure isn't just about raw teraflops and benchmark scores anymore.
Right.
It is about supply chain independence, local data sovereignty, and fundamentally fitting the silicon to the actual workload it's being asked to perform.
So to wrap all of this up and bring it back to the listener,
Yeah.
CortexPod isn't trying to beat NVIDIA at their own game by building a faster GPU. They looked at where AI software was actually heading, these massive, collaborative, multi-agent meshes.
Yes.
They realized the current hardware was structurally mismatched for that future. And so they built a custom distributed brain in silicon, specifically to serve an exploding geopolitically constrained market in Asia that the big players can't easily reach.
This raises an important question, though.
What's that?
If hardware is now being hard-coded at the silicon level to support specialized societies of AI agents working together, how will this change our fundamental perception of AI?
That is the perfect thought to leave you with. In the near future, when you ask an AI to solve a complex problem, you aren't going to be consulting a single omniscient digital oracle waiting on a mountain.
No, you're not.
You will be hiring an entire digital corporation, complete with researchers, compliance officers, and writers, all debating, fact-checking, and collaborating at the speed of silicon. Will you even realize you are talking to a collective rather than an individual?